When you're running the system, you're doing measurements, you never have to get down here into the console. Software controls everything, but you should have some idea of what's here. So this is a Lakeshore product, the model 775. This is the matrix switching for the Hall measurement. You got to move the current source and voltmeters around.
Okay.
And this box also has the high impedance electrometer buffers for when you're measuring very high resistances.
Okay.
So that's all in this box. This is the Lakeshore 475 Gauss meter. It measures the magnetic field that's being applied to the sample. This is the, which one is this? The Key 36485 current meter. So this measures the current. We apply a current and we also measure the current. And so the current is generated by a Key 36220 current source and measured by a 2182A voltmeter. So we always generate a current and measure a voltage. We have no voltage sources in the system. It's always a current source. And this is the temperature controller to monitor the temperature of the sample and control the temperature of the sample. And this is a little power amplifier to run the heaters for heating up the sample. Okay?
Okay. Sí, el escáner y las cuentas. But we control all by software. No tenemos que mover nada.
Sí, ya.
Did someone turn this off?
No.
All right, so this is the icon for the Hall software. This is the configuration utility. You don't normally need to run this, but this says what kind of hardware you have. If you ever added an option to a system, this is where you would come in and tell the system that you bought a new option. But this is your software. When it first starts up, this little warning message comes up. This is a message that's required because you can put up to 100 volts on the sample, and that's a dangerous voltage, so just as a warning that there are high voltages possibly there, so be careful. All right, so there are two steps in defining an experiment. One is you have to tell the software something about your sample. For instance, thickness, and maybe some other things. And then you have to tell the software what kind of measurement you want to do. And then when you want to run a measurement, you take a measurement and you say, I want to run it on this sample. So the samples and the measurements are separate in this software. So up here, I can say I want to define a new sample. And it brings up this box to define a sample. We have Van der Waals samples, which is probably the most common, which we're going to do now. And we have 3 different Hall bar configurations that you can do as well. In the Van der Waals sample, the only parameter that you can enter the thickness. If you keep the thickness at 0, it'll just be sheet values. You can always change the thickness after you run the experiment. So you can run it in sheet values and come back and put in a thickness, and then, you remeasured the thickness and it wasn't quite right, you can come back and change the thickness.
Thickness in centimeters?
Pardon?
The thickness in centimeters?
Well, okay, so the default unit here is meters, but notice this is a yellow box. So that means that it has a special property. For instance, I can say 100 and I can say U for microns, or I could say C for centimeters, or
N for nanometers.
or N for nanometers, or even A for angstroms, if you like to work with those. So you can, or you can put in 196. You can do that as well. But this is where you put in the thickness. You can put in the size of the sample. There's a ASTM standard that says the thickness should be, the size of the sample should be greater than 15 times the thickness. That's just to make sure that the current flow is 2 inch. But you're not required. You can put in a Hall factor. I'm sorry.
This data is not necessary?
Not necessary.
Not necessary.
Not necessary.
It can be 0 or...
Could be 0.
Okay, and another question. We have to select the sample type according to the holder? Or...
No, according to your sample, because I can run on this same card.
According to the position of the contacts?
No, according to the
Entonces,
position
tú
of the
preparas
contacts.
las muestras con esa geometría.
Now notice, if I have a Hall bar, there's a whole bunch more dimensions.
Tú muestras con una mascarilla de capas y la dejas así. La defines de esa.
Pero si son cuadraditas, igual ahí la...
Exactamente.
Como van del pop.
If you do a Hall bar, you need to put in many more different dimensions, because we need to know the size of the Hall bar to be able to do some of the calculations. You can put in a Hall factor. You know what a Hall factor is?
Yes.
A Hall factor. It's technically, it's the ratio of the drift mobility to the Hall mobility. You measure the mobility in a Hall system, you take the same material and do a drift measurement, you'll get a different number. And the ratio of those two numbers are the Hall factor.
What is the Hall resistance? What's the...
No, it's related to the Hall mobility. And it's normally 1. I mean, people normally make it 1 because the true numbers are close to 1 and they're hard to calculate. So you can use 1.
Hall factor?
It's called the Hall factor.
It depends on the geometry of the samples or what?
It really is more to do with the band structure of the sample. If your sample has perfectly spherical bands, then the Hall factor is 1. Okay.
Ahí depende of the symmetry of the measurements?
Yes. Well, not the measurements of the...
And the contact, the size of the contact.
Okay.
But we put 1.
Put 1 in very
Perfect.
You can enter comments here. And just, anything you want when you save it, we save the sample, and anytime you use a sample, it will you'll remember it. If you're running gallium arsenide or aluminum gallium arsenide, we have a depletion layer correction calculation in the software if you want to do that. But it's valid only for those materials, so it's only for running those materials. And I can send you the reference that it's based on. It assumes that the chromium trap level dominates the impurity traps in the gallium arsenide for generating the depletion layer thickness. Basically, the active thickness, okay? I mean, you have your geometric thickness, but then the actual active thickness, the thickness in which the carrier is really moving, can change as the electric field changes. Okay? Basically, you get a gating effect, and that's what this is trying to calculate. So then you can save this for use later. Go ahead. And, oops. That brings us up to 2 o'clock. We want to take a break now,
Ajá.
and then
That's it.
take, come back at 3? Okay. Very good, thank you so much. And we should be able to finish training on the software today, and we'll get the turbo pump running too. So,
Okay.
all right, okay. Anytime. You don't do the easy stuff, do you?
Oh, this is a gold film. This is a...
Pues tengo otra de
Sí, pero estas son las buenísimas.
Ah, pero ya está muy bien.
pero esta hace de
Ah, se ve que...
copper sign.
¿Y la barnizaste? ¿Por qué se ve así?
La estañó con el cautín.
Sí.
Y se llama porque tengo un cifro de cambio. Y ya tiene contactos de
Ya tiene los puntitos, pero ahora